everybody, in this video, this is 9-4. We're going to be talking about conditions for rectangles, rhombuses, and squares. I'm just going to walk through a couple of proofs here. A good part of our work in this section is going to be talking about what conditions are allowed to be known. What combination of conditions do we know that can lead us to certain conclusions? So we're going to start with explain 1. And in this proof in example 1, we're going to be proving that if the diagonals are congruent, then it's a rectangle. So let's look at that. Theorem number 1 is if we know one angle of a parallelogram is a right angle, then we can certainly say that the parallelogram is a rectangle. That is because if we know the parallelogram is a parallelogram, then this angle here is going to be congruent to the opposite angle, of course. And then if the sides are parallel, then the same side interior angles A and B, C and D, and so on would be able to be right angles as well, because they need to be supplementary. So that's the first one. The second one is the one we're going to look at right now, and that is that if we have the diagonals of a parallelogram, and we know that those diagonals are congruent in a parallelogram, then the type of parallelogram that it is has to be specifically a rectangle. And so that's AC is going to be congruent to BD. So as we're looking at example 1 here, we're going to prove that if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. We know because at the beginning here, the definition of a rectangle, the definition of a parallelogram is that the opposite sides are congruent. Then we know AB is congruent to CD. We also know that we're told that AC is congruent to BD. So now take a look with me at this diagram here. Do you see how these segments, let's go back. Do you see how these segments are overlapping from B to D and A to C? And they kind of almost cut through each other. It would be hard to put tick marks on one or the other. So instead of keeping this diagram as just one rectangle, we're actually going to separate it into the top right triangle and the bottom right triangle that are overlapping. So if we put corners on these, this is going to be AD, and this is AD as well. This top corner is B, and this bottom corner is C. And then we can go ahead and put the markings on that we've talked about so far. So we know that AB is congruent to CD, and we know that we're told in the givens that AC and BD are the same. And I hope you can see that AD is going to be congruent to itself by the reflexive property. So let's fill that second piece in there. AD is congruent to AD by the reflexive property. So we can say hopefully that those triangles are congruent. You can see the side-side-side theorem happening there. So there's triangle. And I'm going to zoom in a little bit so I can write a little neater here, so bear with me. So triangle BAD and triangle CDA going in corresponding order by the side-side-side triangle congruence theorem. So once we know that the triangles themselves are congruent over here, then we know that a piece of those triangles are congruent, and the piece that we're heading toward being proving here, if we want this to be a rectangle, hope you can see, is that these two are right angles, because if we have one right angle, we know they're all right angles. So that's where we're headed next. So back over here, we want to know which angles are congruent. It's the right angles that we want to be congruent. So therefore, by CPCTC, specifically, the right angle BAD is congruent to the right angle CDA. So these angles are supplementary, we know, next. And if these angles are supplementary, since they are same side interior angles, then they are parallel. That means that the top and the bottom sides are parallel, so AB is congruent, or excuse me, is parallel to DC in the box there. And therefore, the measure of them adds up to 180 degrees. And so the measure of angle BAD plus, again, the measure of angle BAD by substitution is going to equal 180. And then again, we've got two of the exact same angle BAD is equal to 180, so one of them has to be 90. And then a similar argument shows that the other angles of ABCD are also right angles, or 90-degree angles, so that means that ABCD is a rectangle. So that's filling in the parts of that paragraph proof there with, again, starting with all we know at the beginning is that it's a parallelogram with congruent diagonals, and we can conclude using our side-side-side triangle congruence theorem, using CPCTC, and some substitution that it's also a rectangle. So move on to the next proof, and we have a flowchart proof this time. The givens that we're starting with this time is, yes, it's a parallelogram to begin with, but we want to know that one of the diagonals, this diagonal here that's drawn in AC, bisects the pairs of opposite angles. So angle BCA and angle DCA are congruent, as you can see there. And then on the other end, angle BAC and angle DAC are congruent. So that's our second given. So we're going to fill in the pieces of this proof. Let me zoom in so I can write a little bit easier here. Try to keep the diagram nearby. Okay, so for angle BCA being congruent to angle DCA, that's one of our givens. The second one is the other pair of bottom angles that we are saying is bisected. So that's angle BAC is congruent to angle DAC. And then we see that AC is a shared side, so we'll put those markings on there. Triangle BAC is congruent to triangle DAC. Oh, and we forgot to put a reason over here. Let's put the reason under AC is congruent to itself. Why is that? It's a shared side, so that's our reflexive property of congruence if you want to, but we'll just leave it like that for now. Okay, so what are we able to conclude as soon as we know that we have the triangles congruent? Well, we know with CPCTC or CPCFC, whichever you want to write, that their corresponding sides are also congruent. So that means that BC is congruent to DC, and also BA is congruent to AD. And let's check that diagram again. So now that we know the triangles are congruent, I'm going to change colors here for the tick marks that I can conclude next. We've got BA and AD, and we've got BC and CD. Now that we know, because it is a parallelogram, we know that the opposite sides, DC and BA, are congruent if it's a parallelogram. So technically, each one of these sides actually has double tick marks on it because they're all the same. And so when all the side lengths are the same, with the transitive property there, we can finally conclude that ABCD is a rhombus. Because remember, what a rhombus is a parallelogram with four congruent sides. So that's by the definition of a rhombus. Which has four congruent sides. And that's the end of that flowchart proof. As we go through the problems in your evaluate when you get to class tomorrow, a lot of it will have to do with looking at the given conditions in a diagram and just being able to conclude, as we have through some of these proofs here, what kind of parallelogram we have. Is it able to be called a rectangle, a rhombus, or a square? Okay, see you tomorrow.